Hi all, welcome to the video. In this particular video, we are going to learn about Dijkstra's algorithm. So as part of the Dijkstra's algorithm video, we are going to learn about introduction, like what is the Dijkstra's algorithm, what is the space and basically runtime complexity of Dijkstra's algorithm, what is it based on, and finally I'll run you through the algorithm, like how it works and what all data structure does it use, the primitive data structure, and finally we'll have a code walkthrough. So I'll show you the code for Dijkstra's algorithm and explain it step by step. So as part of the introduction, the first thing about Dijkstra's algorithm is that it is an algorithm to find shortest path between two nodes. So for example, if you take an example of or if you take a sample graph, so say we have a node here, node 1, it is connected to another node, node 2, and this one is connected to some node 4. We have another path here where we have from node 1 to node 3, and node 3 is connected to node 4. So say from node 1 to node 2, if the time taken for us to go from point 1 to point 2 is say 5 minute, from 2 to 4 say it is 4 minute, from 1 to 3 it's 8 minute, and from 3 to 4 say it's like 10 minutes. So these are the time that it takes me to move from point 1 to point 2, point 2 to point 4. So what Dijkstra's algorithm will tell you that if I have to find the shortest path between point 1 and point 4, so it will be the time taken in this path will be 5 plus 4, which is 9. In this case it will be 18. So Dijkstra's algorithm will give you this path and it will tell you that this is the shortest path. Let me erase this and we'll go to the next point. So Dijkstra's algorithm, it follows greedy approach, and when I'll explain the algorithm, that time you will come to know why it follows greedy approach and how it is beneficial. It is based on DFS, that is pretty straightforward. And the runtime complexity of Dijkstra's algorithm is O of V log V plus E. So basically, since it follows greedy approach, so what we do is to implement Dijkstra's algorithm, we use a priority queue or a heap. So if you have to traverse a priority queue, then or add or remove element from priority queue basically, so it takes log of v log v. V is vertex, so number of vertex times log v. So the reason for that is every time you add something in the queue or the priority queue and it needs to be heapified, so it takes log of v time for that. And since you have to traverse all the edges, so that is why there is an additional runtime complexity of plus e here. Space time complexity is order of v because we are going to store all the vertices in the priority queue. And one edge case for Dijkstra's algorithm is that it does not work where you have edge weight which is negative, and we'll come to know about or we'll discuss in detail about this excuse me, when we will discuss about Bellman-Ford algorithm. And Bellman-Ford algorithm, it is used for finding shortest path where we have negative edge weights. So we'll discuss why Dijkstra's algorithm does not work in negative edge weight in the video of Bellman-Ford. So that is all about the introduction. Then let's see how this algorithm works. So let's say we have a graph like this where we have these edges and vertices, and we have this one as the starting point. So let's say we have the starting point as this one. So this is the start for me and this is the target vertex for me. So I need to reach from 1 to 10, and while reaching 1 to 10 I need to find the shortest path between 1 to each of these node that is available in the path. So what Dijkstra's algorithm will do, like I told, it uses DFS and it uses greedy approach, and for greedy approach it uses a priority queue. So the priority queue that will be used in this case, it will be based on the shortest path that has been calculated for the vertices till now. So this will be based on the shortest path of the vertex. So for example, when we initially defined all these vertices, so we did not know what is the start vertex was. So for start vertex, the value of this will be equal to 0. So because from start vertex to start vertex there is nothing much you can do about. So this will have a value as 0, and rest all currently they are infinite distance from source, which is my vertex 1. Now next what I need to do is I need to see all the adjacent vertex of the source vertex. So adjacent vertex of this source is 2, 3 and 4, and the distance of 2 from 1, currently it was initially infinite, but I see a path here which has a value 1. So I have a shortest path between the source to 2, which will be this edge which is connecting 1 to 2. So what I am going to do is I am going to remove this infinity from there, and I am going to put a value of 1. So what this means is that there is a shortest path between 1 to 2, and it will take 1 minute to reach from 1 to 2. So once I have kept this, same thing I need to do for all the neighboring uh, vertices of A or of vertex 1. So similar to that, we will have for 1, 2, 3 also the shortest path will be 1. Initially it was infinity, so 1 is less than infinity. So this will be the shortest path. Same goes for the 4. So this is again 1. Now the trick for Dijkstra's algorithm comes here, because what we need to do is we need to add all of these in the priority queue, and since priority queue is based on the shortest path to the vertex, so we will add vertex 2 and it will have a weight of 1, and next we will have vertex 3, this again will have weight of 1, and we have vertex 4 in our priority queue, and this again has a weight of 1. So these three are there as part of our priority queue. Next what we need to do is we will pull one element from the priority queue. So in this case it can be any one of them, since all the edge weights are same. So for example, let's say we pull 2 from the priority queue. So we pulled 2 out of the priority queue. Let us remove 2 from here. So we have removed 2 from the priority queue. Okay. So once we have removed 2 from the priority queue, next we need to see all the neighbor of 2. So the neighbor of 2 is 5 and 6. So edge weight or currently this was infinity, this was also infinity. So the shortest distance between 1 to 5 currently is infinity, but since we have a edge here, so we'll see the weight is 12 and 1 for the edge weight of 2, or the shortest path between 1 to 2 is 1. So the shortest path to reach 5 will be the minimum of 12 plus 1 or infinity, so which is 12 plus 1, that is 13. So here we can say that this is now not infinity, and even I'll remove this for now, and the shortest path till 5 is a value 13, and shortest path till 6 is again 1 plus 4 or infinity, whichever is minimum. So 1 plus 4 is minimum, so shortest path till 6 is 5. Next, since we have covered the neighbor of 2, so we need to put these in the priority queue. So what we are going to do is we'll add these also in our priority queue. So we'll say that we have 5 with edge weight of 13 and we have 6 with edge weight of 5. So these are in our priority queue. Now this priority queue will heapify itself, and it will heapify based on the shortest path. So shortest path was 1, 1, 5 and 13. So next we will say pull 4 from the priority queue. So when we pull 4 from the priority queue, then we need to move to the adjacent of this. Again this was infinity initially, now the path will be this one plus this edge weight 1. So the shortest path till here will be 2. So again, since we have moved to the adjacent of 4, so we need to add this also in our priority queue. So our priority queue now will look something like this. So we have 6, 5, so 9 will be there next with edge weight of 2, and we did not poll 3 till now, so 3 was there with edge weight of 1. So next when we poll, we'll poll this one because this has the smallest edge weight. So this is the criteria where we are pulling the smallest edge weight. This is the greedy approach which Dijkstra's algorithm applies. So when we go to 3, again this was initially infinity and this will have edge weight of 2. So once we do this, then again we will have the priority queue which will look something like this. We have 9 2, even 8 has a value 2, so it can be added in the end also. So we have a value like this. So similarly it will follow till the end, and finally we'll see that this has edge weight 5 plus 5 which is 10, and from here it is 13 plus 3 which is 16, so minimum is 10. So this will be 10, this will be 12 plus 2 14, 12, 10 plus 2 11, sorry 10 plus 2 12, and 10 plus 1 11. So this will be the minimum of all the paths, so this will be 11. So finally the shortest path will be from 0 to 2, 2 to 6, 6 to 7, and 7 to 10. This is the shortest path between the source and target vertex, and each of these weight denotes the shortest path from source to that particular vertex. So I hope this explanation was pretty clear. I hope you understood how the greedy algorithm is followed in Dijkstra's algorithm. Greedy approach is followed in Dijkstra's algorithm, and the DFS is pretty straightforward. So now we'll jump into the code and see how we can implement Dijkstra's algorithm. This is the same graph which we saw in the theory section, and we are going to find the shortest path for this. So we have defined our edge. It's pretty straightforward definition of edge, like whatever we have discussed in the previous videos of BFS, topological sort, or DFS. It has edge weight, it points to a target vertex. One more thing you can add here, or we can add it in the vertex basically. So as part of our vertex class, we can say vertex has a name, it has an adjacent vertex, so adjacent vertex will be pointed through a list of edges. For example, one has 3 edges, so these will be pointing to a target vertex because edge, it has a target vertex here. Here we need to point one more, we need to have one more pointer which is the previous vertex. The reason for that is once we have computed the shortest path, say from 1 to 10 we computed the shortest path and it was through 1, 2, 6, 7 and 10. The previous vertex pointer will help us to trace the path back in order and time complexity. So that is why one more pointer is required. Boolean visited is there, it might not be required in this case, but since this vertex was that existing one, so I used it. And minimum distance, so minimum distance is basically the distance of this edge from the source, each of these edge from the source. So when we initially create minimum distance, it will be infinity for all, and once we define the source, which vertex is the source, then accordingly we'll calculate the minimum distance for each vertex. Now next thing that is important is this priority queue. So for priority queue we have defined a comparator which is based on the vertex min distance. So this min distance is nothing but the min distance of this edge, this vertex from the source, and it will be used for comparing. So what if this seems tough to understand, this can be very simply written as, say I have got two vertex to compare, A and B. So what I need to do is I need to compare the minimum distance of A minus P dot, get minimum distance. So this is what we need to do. So this is to write it in simplified way. We can simply say that, okay, you replace it with comparator and this IntelliJ help us to do this, or you can write it on your own. But the important point is this priority queue here, it is based on, or the comparison or the heapification of this priority queue will be done on the minimum distance of the vertex that has been added in the priority queue, and this is the priority queue of vertex. Okay, so as part of calculate shortest path, so what we need to do, we need to have a source vertex. Source vertex will set the minimum distance as 0 because this is where we are starting, and we'll offer the source vertex to our priority queue. So we have added that here. Now this algorithm will go on till this priority queue is not empty, and which is self-explanatory because we need to visit all the vertex that is connected to the source vertex. So suppose there is no connection after this part, so say after this point in time there is no connection, all these are not there, say, then in that case we only need to traverse the graph from 1 to 2, 3 and 4, that's it, and that is what the shortest distance will be calculated for. So that is why this algorithm will go as long as the priority queue is not empty or we have something to process in our priority queue. Next we will have the starting vertex. So starting vertex will be whatever vertex is there in the in our priority queue. So initially we have just this one, like I explained in the theory section. So we'll poll this and we'll go to each of the adjacent vertex of this particular vertex. So the vertex V in this scenario will be the first vertex can be 2, 3, 4, any one of these, and what we need to do is we need to check if u dot get minimum distance. So this is vertex u, get minimum distance will give me 0 because we have set it to 0, and there is a edge weight. So for this edge the weight is 1. If this is less than v dot get minimum distance, so v in this scenario will be, let's say, this vertex which is 2. So initially when we created the vertex, like you saw, we have set the value as maximum, which is infinity. So this minimum distance of u is 0, edge weight is 1, and this is infinity, so definitely this is less than this, the v dot get minimum distance. So what we are going to do in this scenario is we'll set the minimum distance to whatever we got here on the left hand side. To simplify this, we can simply say, we can create something of a variable here, and we can say int temp distance is equals to this, and we can compare the temp distance, and if the temp distance is less than the destination's minimum distance, then you set the target vertex minimum distance as the temp distance. And once we do this, we need to set the previous vertex to u, since this is to trace that the target vertex v minimum distance is coming from the uth vertex. So to understand it in the graph sense here in the picture, so when I set this as 1, the minimum distance of vertex 2 from source as 1, I need to set the previous vertex of 2 to 1, so that when I backtrack I can identify that the minimum distance of 2 is coming from 1. And once I have said that, I need to add now 2 into my priority queue. So I will add this 2 also in my priority queue, which is exactly what we are doing here, and the algorithm will keep on going. So next time I have, like in the theory section I showed you, the next set of vertices, we have 2, 1, then we need to add, okay, we have 2, 1 here. After that we have not visited anything, or this loop, basically this edge loop will continue. So after 2, 1 it will add, like say 3, 1, and then it will add 4, 1, like that. Okay, now once this for loop is complete, then we will poll the next vertex from the priority queue. So in this case, example was like we polled 2 from there, which will be polled, and then we'll go to the adjacent of 2. So we'll visit this 5 and 6. So that is exactly same as what we explained in the theory section, and we'll keep on adding all the vertex in the priority queue, and priority queue will make sure that those vertex are pooled in the way where we have the minimum distance at the head of the queue, so that when we poll we get the vertex which has the minimum distance till now, and that is what follows the greedy approach. So once we have done that, so I've written a small this one to print the shortest path, small method for that. So once we know which is the target vertex after all the minimum distance and this previous vertex has been set, so I just need to backtrack, like as long as, so for example for this case there will be no previous vertex, so because this is my source, so I will traverse the target till the target is null, and I will say target dot get name, and it will print the path. And finally I will print this path in my output. I am building the path here basically. So let us run this and we'll see. In the theory we found out that shortest path was from 1 to 2, 2 to 6, 6 to 7, and 7 to 10. So even in this case it is printing the same path, 1 to 2, 2 to 6, 6 to 7, and 7 to 10, which is this same path. And if you want, you can add the distance here also, that what is the minimum distance of the target. So that is it for Dijkstra's algorithm, and I hope the explanation of Dijkstra's algorithm was really clear and you are able to understand it now. So goes for the code. So I hope the code is pretty simple and straightforward, and you will be able to solve some problem based on Dijkstra's algorithm. In the next video, we are going to solve a problem based on Dijkstra's algorithm, and then we'll move to Bellman fault algorithm. So that is it for this video. See you in the next one. Take care. Bye.